Hi, my name is Ibrahim, and today my partner Praneeth and I will be discussing aligning LLMs with RLHF and RLAIF. So, large language model pre-training has evolved through self-supervised learning on massive text datasets. Instruction tuning was added to help models better handle human queries. ChatGPT, Claude, and Llama are examples of the progress in this domain, but key challenges still persist. Models can generate harmful content and generic responses. Supervised fine-tuning, which is basically behavior cloning, reinforcement learning with human feedback, and with AI feedback are common fine-tuning methods to improve model behavior. RLHF requires a human in the loop, while RLAIF uses LLMs to annotate, which decreases cost and disagreements. RLAIF has achieved promising results recently, and it shows that it is a scalable alternative to human annotation. So we use three models in our work. The Mistral 7 billion uses a sliding window where instead of attending to all previous tokens, which can get computationally expensive, each position in a layer only looks at a window of 4,096 tokens before it. An instruct model was trained by fine-tuning on instruction datasets publicly available. The Mistral 7 billion the 7 billion instruct has built-in content moderation abilities where it uses a self-reflection mechanism to classify content into several categories such as illegal, hateful, harassment, and violent. It completes this task with a 99.4% precision and a 95.6% recall. The T5 base model uses an encoder-decoder transformer model, and its key feature is that it is very versatile due to its text-to-text framework that unifies different NLP tasks. The BERT model uses an encoder-only transformer model where it learns by predicting masked tokens and determining if two sentences follow each other. Our goal here is to generate synthetic data using an LLM to train smaller models with reward optimization. Our work currently builds upon the previously patented work by my co-author, Praneeth, but with a much more sophisticated method of applying reward optimization for better results. We use 5 datasets for our task. We use LoRa, lower rank adaptation, for efficient fine-tuning using standard supervised fine-tuning. We use a Roberta-based toxicity detection model, which creates a proximal policy optimized ready model by adding a value head to the fine-tuned model. We implement reward computation using the toxicity model, then we generate summaries using the current policy and evaluate toxicity on these generated summaries. We update the model using PPO to reduce toxicity while maintaining summarization quality. We test our hypothesis using different baselines.
And now we'll be talking about the process involved as part of the final research project for the course. To begin, our entire process is very generic, but as part of this project, we focus on proving our hypothesis using two entirely different natural language tasks of summarization and NER using PII. The whole process works in three different phases. The first phase is the capturing the data from the Hugging Face and training the models of F95 as well as the BERT model and evaluating them on these metrics that we have selected and creating the baseline metrics. Now, the same workflow is again parsed separately in order to do the prompt modeling and instruction tuning of the Mistral 7B model with the help of PPO objective to further reward optimization steps. We utilize the parameter efficient fine tuning to leverage the resources as well and to fine tune this large model. And KL divergence penalty and reward models are used in order to do the reward hack in order to do the reward hacking as well as the optimizing the models efficiently. Once the PPO optimization step is done, we essentially generate the synthetic data as part of the fine-tuned Mistral model and utilize this particular data on the already fine-tuned BERT and Flantify models as part of the from the phase 1 as part of the phase 3, and we again evaluate it on the similar metrics. Now I will do a small code walkthrough of the PPO. This is how we essentially initialize the model, construct the data set, as well as do the LoRa fine tuning and create the reference model and load the evaluation metrics in this particular format. We also define certain helper methods to help us during the fine tuning phase. And this is the code for where we essentially model and train the whole process. Now, for the results part from the model, as we can see on the right hand side, the reward for them is essentially pretty huge when compared to the left hand side, which is the reward before the RL efficient fine tuning. And the similar thing can be observed in both the summarization as well as the PII task. The hypothesis testing that we have done shows that our RL updated Flantify and RL updated BERT are essentially having a much more higher scores than all the metrics that we have selected. So the key takeaway is that this approach is scalable to any kind of natural language task, not just limited to NER or summarization. And the small language models can now be as powerful as large language models, reducing the need for heavy compute and thereby saving huge costs on use case specific tasks. So thank you, and feel free to reach out with any questions.